Welcome to The Explainer. You ever stop and think about how the perfect material gets chosen for, say, your phone or your car, or even just a kitchen spatula? Well, I can tell you it is definitely not a lucky guess. Today, we're going to pull back the curtain on the really rigorous engineering process that finds exactly the right material for any job. All right, so here's our game plan. We're going to start with just how huge this problem is. Then we'll dive into the systematic process engineers use, see how they filter down all those choices, and then we'll get into the crucial art of compromise. After that, we'll look at how they refine their designs, and finally, we'll see how this whole thing shapes the world we live in.
So first things first, let's just try to get our heads around the massive scale of the challenge that every single designer and engineer faces at the beginning of a project. I mean, it is frankly a little overwhelming. Thanks to a century of incredible material science, engineers have a staggering number of options to choose from. Some estimates put it at over 80,000 different materials, and each one has its own unique fingerprint of characteristics. You know, strength, flexibility, cost, you name it. It's truly an ocean of possibilities.
So that just begs the question, right? When you're faced with this huge library of possibilities, how do you ever land on just one choice? Is it just years of experience and a really good, educated guess? Or is there an actual method to the madness?
Well, you guessed it, the answer is a highly structured process. This is not about intuition. It's a workflow that systematically balances three critical, interconnected elements to find the optimal solution, not just one that kind of works.
And this picture illustrates the core idea perfectly. I want you to think of it like a trinity. You've got the design of the part, the properties of the material, and the process you use to make it. You absolutely cannot decide on one of these without thinking about the other two right from the get-go. They are totally inseparable.
So the crucial takeaway here is that engineers have to weigh all of these things at the same time. For the design, they're asking, okay, what does this thing actually have to do? For the material, it's what properties does it absolutely need to have? And for processing, how are we going to make this thing efficiently? And did you notice the one word that pops up in all three? Cost. That's the constant underlying reality that ties everything together.
Now let's see how this whole idea builds into a process that looks kind of like a funnel. This is how engineers take that entire universe of over 80,000 materials and systematically filter the options down to just one.
So it's a pretty well-established four-level approach. You start at the top, super broad. At level 1, is this thing going to be made of metal or plastic? Then level 2 gets into the process. For instance, are we going to cast it by pouring molten metal, or are we going to shape it from a solid block? Level 3 narrows it down to a specific family, like say stainless steel. And finally, level 4 gets super specific, right down to the exact grade and specification number.
Now, what's really cool is how this whole filtering process maps directly onto the product design journey itself. See, early on, in the concept phase, you're just making those big, broad choices. As the design gets more concrete, what they call the embodiment phase, you're using more precise data to narrow things down. By the time you get to the detail phase, you're using the highest resolution data to pick out that one single specific grade of material.
But here's the thing. Finding the right material isn't about finding a perfect one. Because a perfect material, it rarely, if ever, exists. The real art of engineering is finding the material with the right set of compromises for that specific job.
In fact, you'll see this stated explicitly in engineering textbooks. Trade-offs aren't a sign of failure. They're a fundamental, totally unavoidable part of the process. Think of it this way. Pretty much all material properties are connected, so when you pull a lever to improve one thing, another one almost always moves in the other direction.
Okay, a classic example is the trade-off between hardness and toughness. So let's say you heat treat a piece of steel to make it harder. That also increases its strength, which is great, but you almost always decrease its toughness, which means it gets more brittle and is way more likely to shatter if you hit it hard. See? You can't have it all.
And these trade-offs are everywhere you look. A stronger material might be less flexible. A super high-strength steel might be a nightmare to weld or machine, which drives up your manufacturing costs. It's this constant balancing act. Sometimes, a material that looks cheap on paper can end up being way more expensive in the long run because it's just so difficult to work with.
So, if every single choice is a compromise, how on earth do engineers navigate all these complex trade-offs to find the best possible solution? Well, they don't just guess and hope for the best. They use a really powerful cyclical method.
It's a concept called guided iteration, and it is the fundamental engine of engineering design. You define the problem, you cook up a few potential solutions, you evaluate how well they actually work, and then, and this is the critical part, you use what you learned from that evaluation to redesign and make it better. Then you do it all over again.
And this is not a one-and-done kind of thing. This loop is repeated hundreds, sometimes even thousands of times on a single project. You can see it in this flowchart. There are these little iteration loops within the big picture conceptual design, more loops when you're configuring the components, and even more when you're finalizing all the dimensions. Each cycle just keeps refining the solution, getting you closer to that perfect balance of all those competing demands. Okay, let's zoom out for a second and connect this really methodical, iterative process back to the world around us. Because the payoff for all this painstaking work is, quite literally, everywhere you look.
The reason your smartphone is both lightweight and somehow durable enough to survive a fall, or why a modern car is both incredibly safe in a crash and still affordable for most people, that's a direct result of guided iteration. It's the hidden method that balances all the necessary trade-offs to create the amazing, optimized products that define our modern lives.
And this leaves us with a really fascinating final thought. We're now entering an age where AI can act as a co-pilot for engineers, where it can run thousands of these iterative cycles in the blink of an eye. So how will these incredible new tools change this deeply human process of navigating compromise to build our world? Well, that's a question engineers are just beginning to answer.